for this DB9 connector, pin number 2 and pin number 3 is there. So what is pin number 2 and pin number 3 of DB9 connector? Pin number 2 is receive data and pin number 3 is transmit data. That means pin number 2 will be receiving the data and pin number 3 will be transmitting the data. And we are using a line driver, right? So the line driver is MAX232 and we are connecting that to pin number 14. Pin number 2 is connecting to pin number 14. And what is pin number 14? It is transmit 1 out. So how is this connection? We have our computer. Okay. Computer, we have a receive pin. Computer receive pin, which is connected to the transmit out pin of the MAX232. Okay, there is a MAX232 here. Okay, for this MAX232, the transmit 1 out is connected to the RxD pin of the computer. Computer in the sense DB9 connector of the computer. Is it? Okay. Now, the other side of this MAX232 IC. If you see the other side of this MAX232 IC is connected to pin number 11, right? Yes, the other side is pin number 11 here. Okay, and pin number 11 is connected to P3.1 of the 8051. So what is pin number 11 in the MAX232? It is transmit in. So I will write here. Pin number 11 of MAX232 is transmit in. Okay, or T1 in. Now that is going to be connected to where? It is connected to the pin number 3.1, that is pin number 11, okay, or P3.1 of 8051 microcontroller, that is a transmit pin. Okay, so you have on this side 8051 microcontroller which is having a transmit pin, that is P3.1. Here it is transmitting. Okay, suppose if it is transmitting 1. For 8051, it is a TTL logic and a 1 is represented by, logic 1 is represented by approximately 5 volt. Okay, now that is going to be the input of this MAX232 line. There is a MAX232 IC here. Okay, on the MAX232 IC, one of the input, that is pin number 11 is the input, right? This is a, it is going to the transmit 1 input, right? So this output, whatever the 1 is transmitted, suppose if I am sending 1 here, that means a 5 volt will be going to the transmit in of this MAX232. So this will become 5 volt. At the output of MAX232, this is what we are transmitting is 1, right? So the 1 is represented by a voltage level between -3 to -25. So the moment a 5 volt appears at transmit in, this T1 out of the MAX232, that is at this point, you will get some value. So for example, let us say around -15 volt we are getting, something in between, -15 volt, okay? And this -15 volt is considered as logic 1 in RS232 transmission, right? So that means at this computer, we have an RS232 logic is deployed in this computer because of this DB9 connector, and to the input of what it is receiving at the RxD pin of this computer DB9 connector will receive -15 volt. So what you have transmitted? You have transmitted a 5 volt. You transmitted a 5 volt, and at the computer input you are getting a -15 volt. So transmitted 5 volt, at the computer side you are getting -15 volt. Yes, you have transmitted logic 1 as per TTL, you have received logic 1 as per RS232 connection. So this is the need of, or this is the significance of this line driver MAX232 IC. Similarly, if you see, while receiving also, what you will be receiving is what is transmitted from the transmitted from the DB9 connector. Suppose if you are transmitting a 0 here, if you are transmitting a 0 in the DB9 connector, you know very well a 0 is represented by any range between +3 to +25. This is a 0, right? To +25. So let us assume, for example, 15 volt is what you are transmitting at this point. So you transmit 15 here. A 15 will appear at the line driver input, and that will convert that 15 into 0 volt at the output of this line driver, and the controller will receive it as 0. Understood? So you are sending logic 0, you are receiving logic 0, but you are sending voltage level 15, you are receiving voltage level 0 volt. Okay, so this is how the MAX232 signal, the MAX232 IC is working when it is used in between 8051 and a computer to communicate through RS232 protocol. This is about the MAX232 line driver IC. Okay. Now we will go through the next important thing before doing the programming. So as we have seen, we know that 8051 takes care of serial communication also, and we have two dedicated serial communication channels for 8051, that is TXD as well as RXD, right? And 8051 is using asynchronous transmission, serial communication, right? And so we have certain things which is defined in the asynchronous transfer or asynchronous serial communication. The one of that was a baud, or what is a baud rate, and there are some standard baud rates which is defined in a computer. The standard baud rates are given here, that is 110, 150, 300, like that. These are the standard baud rates, and in this standard baud rate, in generally we will be using maximum this 9600 baud rate in most of our communication. Okay, so this is the important baud rate we should be always remembering. However, in order to generate this baud rate, we will be using 8051 timers. Okay, so when you talk about this 8051 serial communication, there are few registers. There are few registers which is associated with the serial communication. One is this SBUF register. Okay, SBUF or serial buffer register, and the second one is the SCON register or serial controlled register. Okay, these are the two registers associated with the serial communication. SBUF register, as it described here, it is an 8-bit register which holds the data to be transmitted or the data which is received. Okay, so it's a it is just holding some 8-bit data. You know very well, for a serial communication, when it is an asynchronous transmission, you know, other than this 8-bit data, we have a start as well as stop bit. Then you will be having this parity bit. There are so many other header files or other than the data itself, right? So in that, the data part of this 8051 data part of this serial data will be stored in the SBUF register. So if you need to transmit, for example, if you wanted to transmit a data through the TXD line, then that data has to be placed in the SBUF register. Okay, that is the first thing. Okay, the moment you put any 8-bit data to the SBUF register and start the serial communication. How do we start the serial communication? Is basically starting the timer which is responsible for the serial communication. So you know very well how to start a timer also, right? So what you need to right now understand is, the moment a data is kept in this SBUF register, the data will be transferred via the RXD line. Okay, The moment it is kept in the SBUF register, it will be transferred via the TXD line, provided the timer responsible for the serial communication is already running. Okay, that means that TR bit is set. TR bit is set. Similarly, okay, while receiving also, okay, whatever the data which is being received by the RxD line will be stored in the SBUF register. So you remember one thing, there is one SBUF register which will be used for transmitting the data as well as receiving the data. However, you have got instructions to copy that value from the SBUF register to the accumulator and then perform it. And that can be done using this method, right? So if you wanted to store a data to the SBUF register, just like any other register, SBUF is also a special function register. You write move SBUF comma hash some data. Okay, this is if I wanted to send the letter D through the transmit TXD channel, then I should simply write move SBUF comma D. If all the settings are done properly, then the moment this is moved to the SBUF, the transmission will happen. Okay. Suppose if you wanted to move, instead of directly doing this, this is an immediate mode, right? You can also move the content of accumulator to also to the SBUF register. Okay. This is for transmitting. Remember, while transmitting the data, the SBUF is your destination, and the data to be transmitted should be moved to the SBUF register. But while receiving, SBUF is the source, right? While receiving, you need to take the data from the SBUF, which is already filled by the value which is coming through the RxD pin. Okay, and that is SBUF is filled already, and that will be moved to the accumulator. So this is what is the how we will be reading or writing the SBUF register. The moment you place the data to the SBUF register, it will start transmitting. It will not wait for anything. But that is provided the timer is running already. Okay, that means, see, there are certain conditions, that is, there are certain prerequisites for the serial communication to work. The first thing is we need to know what is the serial baud rate, and we need to see what is the mode at which this serial communication is working. And once we set all these things ready, then we will start one timer. Okay, and this timer will be responsible for creating this particular baud rate, and generally we will be using timer 1. Okay, so that means timer 1 will be acting just like any other timer what we have learned in the previous class. We don't have a separate SBUF register for transmission and a separate SBUF register for receiver. We have only one SBUF register, and internally the microcontroller will take care of whether it is to be it is a received data or whether it is data to be transmitted. Okay, this is the idea. Now coming to the next register. So I told you there are two registers. That is serial buffer, we have already seen, that's a special function register. There is one more register, that is SCON register. Similarly, like our TCON register for the timer explanation, there is a serial control register, and this is also, there's an 8-bit register here, and we have serial mode bits SM0 and SM1 serial mode, and there is also one SM2 which we generally don't use it for the multiprocessor communication, and there is a receive enable, and these two bits TB8 and RB8 is the bit 8 generally they say, which is not widely used again, and then there is a transmit interrupt and receive interrupt. So these are the 8 pins. So what we will do is we need to basically understand the functionality of SM0 and SM1, the serial mode, and REN as well as this TA and RA. That is only we will be studying in this, because we need to basically understand how to, if you see the syllabus, we are studying how to send a program or how to receive a program, writing in a C or assembly, right? So anyway, I will just explain this one by one, the serial mode, REN and TARI. So in the SM0 and SM1. SM0 and SM1, which is basically used for controlling the serial mode. Okay, so there are 4 modes: serial mode 0, 1, 2, 3. We will see whatever is a required mode in our explanation. Generally, most of the time, that's why that description is clearly given here. We will be using serial mode 1, okay, in our communication. So please remember, for a serial mode 1, which is in that serial mode 1, it is 8-bit data, 1 stop bit and 1 start bit. SM2 bit is used for multiprocessor communication, and we have a receive enable. Okay, the receive enable, when it is high, it allows 8051 to receive the data from the RxD pin. And we have another 2 interrupts. So again, as I said, this transfer bit 8 and receive bit 8 is also not widely used, which is generally like as I told you, that either we have got either 8-bit data or the 9-bit data. In such cases, that extra data, whether to be transmitted, that bit will be stored in this particular position, because normal data size is only 8-bit. If everything is configured properly and the serial communication is ready to happen, then the moment you write this line, that is move SBUF, comma, some value, suppose something like n, my name, or some value, the moment you move this data to the SBUF register, this data will be transmitted to the TXD pin. If this character is transmitted, once this character is transmitted through the TXD channel or TXD line, then this transmit interrupt will be high. Okay, so that means once the transmission of a particular character is over, then the transmit interrupt will be high. So you can just read through this. When 8051 finishes the transfer of an 8-bit character, it raises the TI flag. Similarly, RI also. When you are ready to receive something and it is coming, the data is coming to the 8051, when this RI will be high, when the reception is over, when receiving the data is over. Okay, with this understanding, in order to begin the programming, you must remember that these are the standard baud rates. So we will be talking about basically I need to see, as I told you, that to generate a baud rate, what we are using is, we will be using a timer. Okay, and the timer which we will be using is timer 1 of the 8051. Okay, so in order to count any pulses, you know that there should be a initial value to be loaded to the timer, right? So let us understand what should be the initial value loaded to the timer in order to generate this kind of baud rates. Okay, these are all fixed baud rates, so we cannot change. I cannot have my own baud rate like 5000 baud rate. No, that's not possible. Okay, so there are fixed values. Either it is 4800 or then 9600. So in order to generate that speed, what should be the initial value to be loaded on the timer register? So there is a calculation for that. Before that, we will do that calculation with the help of this example. So what this example tells is, if the crystal frequency is 11.0592 megahertz, find the TH1 value needed to generate the following baud rates. There are 3 baud rates given. Okay, what you need to understand, one thing is that in serial communication, this timer, we are using this timer 1. Okay, and this timer 1 will be used with 8-bit auto reload mode configuration. Timer 1 in the 8-bit auto reload mode. Okay, so 8-bit auto reload mode, when you are using it, you know that you need to store the value only in the TH register. That is what we have studied in the TH, in the timer topic, right? We need to use the timer 1, which is in the mode 2. Timer 1 in mode 2. Mode 2 is 8-bit auto reload mode, right? 8-bit auto reload mode. And since we are using timer 1 in 8-bit auto reload mode, the initial value you can always store in the TH register, right? Because TH register will copy this content to the TL register, and the TL register will start counting once the timer run bit is set, right? So this is how the timer 1 will work in 8-bit auto reload mode. So what you will be doing is, in this example, you are going to find out what is the value to be initially loaded to the TH1 register in order to achieve this 9600, 2400 or 1200 baud rate. Okay. So here the calculation is like this. It's a very simple calculation. Like your timer clock. So if you remember in the timer chapter we have seen, a timer clock, okay, is exactly equal to 1 machine cycle or the master clock divided by 12, right? Master clock divided by 12 was actually your timer clock. Similarly, you have a serial clock, okay? It is timer clock divided by 32. That is a serial clock. So when we are using this timer in this for the serial communication, that timer will be counting the clock in this rate of the serial clock only. For example, if we take an example, suppose if the timer clock is master clock, let us take an example. Suppose master clock is 11.0592 megahertz. Okay, you know the timer clock will be yes, timer clock is 921.6 kilohertz and serial clock is timer clock divided by 32. You got 28,800 hertz, right? This is what you got, 28,800 hertz. So now you see 28,800 is the frequency at which that serial clock is running. That means, what is the time period? Can you tell me? The time period is 1 divided by 28,800, right? So 34.7 microsecond is the time taken for the one clock period, one serial clock period, right? Now my question is, I am telling my baud rate. My baud rate is 9600. If I say baud rate is 9600, in the signaling method what we are using, the baud rate and bit rate all will be same only. So we can say it is same as your frequency is 9600. So when I say 9600 is the frequency, what will be the time rate of this particular transmission? That is 1 by 9600, right? How much it is? 1 by 9600. So we will be getting approximately 104.1 something microseconds. So what I wanted to say to you is, to be very clear, I have told you that this timer, okay, we are using timer 1 in mode 2, that is 8-bit auto reload mode for serial communication. That's what we said. What's the time now? 12:34, right? Yeah. So we are using timer 1 in mode 2, 8-bit auto reload mode, and we know that this timer is working with a clock frequency, that is the serial clock frequency, right? Serial clock frequency is the clock frequency by which this timer is working, and that clock frequency is 28,800 hertz or 34.7 microsecond is the time period of that particular clock. That means each count, if you remember your earlier classes, each count of the timer takes 34.7 microsecond, right? And if we need to achieve a 9600 baud rate, to achieve a 9600 baud rate, what should be the time period for each communication? It is 104.7 microsecond. That means how many counts are required to reach 104.7 microsecond? The count is 104.7 microsecond divided by 34.7, and this will become exactly 3. So basically you need 3 counts to lapse to get this baud rate of 9600 or to get this time period of 104.7. That means we need to load a value. This is which timer and which mode? Timer 1 in 8-bit auto reload mode, right? So the calculation of the initial value to be loaded is what? FF is the maximum because 8-bit. FF minus the initial value, okay? FF minus the initial value plus 1 is equal to 3. So what should be the value to be loaded? It is FD. FD will be the initial value to be loaded. FD corresponds to minus 3. If you need to get a 9600 baud rate, you need to load FD to the TH1 or you need to load minus 3 to TH1. So you can just directly say that you will load minus 3 instead of you don't need to really calculate all this complicated thing. Okay, so how do you get the calculation for each baud rate? What should be the value loaded is now we can easily find out. See, we can also get this value 3 just by dividing your timer serial clock. Serial clock was how much? 28800. 28800 divided by the required baud rate. Required baud rate is 9600. So when you do this calculation, whatever value you are getting, that many count are required to be counted, or minus of that value will be the initial value to be loaded. So with this idea, we can just go back to this. You see, I need to generate 9600, 2400 as well as 1200. The value to be loaded is very simple. 28800 by 9600 is 3. So the value to be loaded is what? Not 3, it is minus 3. You should write something like this. Move TH1 comma minus 3. What are the remaining values? How much is 28800 divided by 2400? You will be getting here 12, and 28800 divided by 1200, 24, right? So that's what. So if you see, if you write move TH1 comma minus 12 or move TH1 comma minus 24, this is how the initial value to be calculated for a specific baud rate, provided this is the frequency. So now you see why this 11.0592 megahertz. So that is the frequency where we will get exact count like this, right? If you take 12 megahertz instead of 11.0592 megahertz, we will not be able to achieve this 9600 baud rate, because when you take 12 megahertz, we will not get this 28800, is it? And this will, instead of 3, we will get a fraction. So that means we cannot and we can't put a fraction in this TH register, right? So we will never get this 9600 baud rate if we were using this 12 megahertz. That is the reason this odd value of 11.0592 megahertz is being widely used as the timer clock, I mean the master clock for 8051. If you see for all these values, this 9000, all these values are integer multiples of that 11.0592. I mean, if you expand this, all these values will be integer multiple of this only.